To keep a mid-size helicopter in the air, operators burn through roughly 50 gallons of aviation fuel every hour. That translates to an operating cost of about $200 an hour, strictly for fuel. An electric rotorcraft, by contrast, draws power at a cost of roughly 8 cents per mile. This fuel inefficiency leaves a $49 billion global helicopter market vulnerable. The industry relies on a high overhead economic model that has remained largely unchanged for decades. The high costs trace back to a mechanical problem. Traditional helicopters rely on complex gearboxes and combustion engines containing thousands of moving parts. Every linkage is a potential single point of failure that requires constant, expensive inspection. These mechanical requirements create astronomical maintenance bills and an intrusive 87 decibel acoustic profile. Because of that noise, helicopters are largely restricted from operating high-frequency routes in urban areas. Since legacy aviation cannot scale to serve the average commuter, the daily transit burden remains entirely on the ground. This leaves major highways in a state of perpetual gridlock, while the airspace above them sits underutilized. Traditional helicopters are trapped by their own mechanical complexity. They are too expensive and too loud to offer a viable alternative to ground-level congestion. Electric propulsion solves the mechanical problem by replacing turbines with simple, distributed motors. This design removes complex gearboxes and many of the maintenance-heavy components found in traditional rotorcraft. This 3D chart tracks the evolution of battery energy density. To beat gravity, battery technology needed to reach a 300 watt-hour per kilogram threshold, allowing aircraft to carry multiple passengers while projecting a 75% reduction in maintenance costs. The Joby S4 is one of the first aircraft utilizing this distributed propulsion in flight tests today, proving electric motors maintain stable, quiet flight. These electric motors also address the noise problem. At cruise altitude, an electric air taxi registers roughly 45 decibels, a level effectively imperceptible against the background noise of a modern city. Electrification shifts the fundamental unit economics of flight. By removing the high maintenance and fuel costs of traditional turbines, air travel becomes price competitive with premium ground transport. Taking these aircraft from testing to commercial service requires an entirely new class of ground infrastructure. These hubs, called vertiports, must be integrated directly into dense urban centers to be useful. Dubai established the global flagship for this infrastructure, completing the world's first commercial vertiport, built as a primary hub integrated into their international airport. This visualization overlays the operational blueprint of the hub. To generate a return, the facility targets 170,000 passengers and 42,000 aircraft movements annually. Achieving that volume requires ultra-fast electric charging to minimize idle time on the ground between flights. Paris is taking a different approach to integration. Rather than purpose-built hubs, they are using the city as a testbed for blending these low-altitude flights into existing conventional air traffic patterns. The active construction in Dubai and Paris proves advanced air mobility has moved past the experimental stage and into the realm of major public works. Even with the technology and infrastructure in place, the industry faces its most complex challenge in government certification. In the United States, the FAA is currently developing the first performance-based framework to certify that these aircraft are safe for the general public. In Europe, EASA is pursuing a parallel effort, though they are utilizing a stricter, prescriptive set of safety standards for every component of the aircraft. Because no blueprint for electric aviation exists, the pioneering companies must help write the safety rules as they go. This creates a first-of-type penalty, a massive financial burden for the companies that get to the finish line first. This line graph illustrates that penalty. Early leaders spend between $1.0 and $1.5 billion per aircraft to navigate certification. But establishing this regulatory pathway triggers an exponential surge. Once certified, the global market is projected to reach $87 billion by 2034. The high cost of entry today serves as a gatekeeper for the market. These certification billions are the price of admission for companies aiming to control the urban flight networks of the next decade.